Okay, welcome back, Mathcounts friends. Today we're looking at the chapter sprint round from this year, 2025. It was just released, and I went through in part one, I went through the 15 easier problems, and this one I'll be looking at the 15 harder problems. I encourage you, as always, to pause the video when you see a problem and try to work it out on your own before you look at the solution. Let's jump right in. All right, problem 16. This one says that we have a water tank in the shape of a rectangular prism, and it has dimensions 10 feet by 3 feet by 2 feet, and it's oriented with top and bottom surfaces being level. And it says at 11 a.m. the water level is at 70%. Okay? And the water level begins draining from the bottom of the tank at a constant rate. And at noon, the water level is down to 40%. Okay? And then at 1 p.m., that's an hour later, it wants to know how many cubic feet of water are left in the tank. So we can see from 11 a.m. to noon that we lost 30% during that hour. And so during the next hour, since it's at a constant rate, we should lose another 30%, which will bring us all the way down to 10%. But we need to know what that 10% is in cubic feet. Fortunately, the height of this tank is 10. So if we're at 10%, the height of the water is just 1. And so the volume in cubic feet is going to be 2 times 3 times 1, since we have this box of water here that's 2 feet by 3 feet by 1 feet. So that's going to be 6 cubic feet of water at 1 p.m. All right, let's go on to the next one. So this one says the prime factorization of 2025 can be written in the form a to the b times c to the d. What is the sum of a plus b plus c plus d? Now, you should always memorize the prime factorization of the current year. In this case, it's 2025, and it has a really great prime factorization because it's a perfect square. So 2025 is equal to 45 squared, and of course 45 is 3 squared times 5. So this is going to be 3 to the 4th times 5 squared when you do 45 squared. And so from this, we can compute this a plus b plus c plus d by just adding up all these numbers. 3 plus 4 is 7, 5 plus 2 is also 7. So we're going to have 14 when we add those four numbers up. Another cool thing is that 45 is a triangle number. So this is actually the sum of the first 9 integers squared. And that means that 25 is actually the sum of the first 9 cubes. So that's pretty cool. All right. Let's go on to number 18. This one says Vera begins at the center square, this one here, in the grid shown, and moves from square to square in such a way that she only moves to a square that shares a side with her current square as she visits each square exactly once. What is the sum of the 4 possible distinct values for the sum of the first 4 squares she will have occupied, including 5? Okay, so she starts at 5. She can go to any one of the neighbors, 2, 4, 6, or 8. And then if you think about it, like if she goes to 6, for example, then she's going to have to go to 9 or 3. If she goes to 9, she goes to 8. If she goes to 3, then she'll go to 2. So the first 4 numbers she will have visited in those 2 cases are, in one case, these 4 numbers, right? If she goes 5 to 6 and then to 9 and then to 8. And in the other case, she will have gone and visited these 4 numbers here, right? And if you go through and think about the other neighbors that she could choose, not just 6, but you could think about 2 and 4 and 8, you'll realize that those 4 sums are just the sums of the 4 values near these 4 different corners, right? So centered on these 4 points, you're going to have 4 different sets of 4. So for example, you'll have one other one here, and you'll have the last one over here, right? And so if you add those 4, think about adding these 4 and adding these 4 and adding these 4 and adding these 4. You're going to add the 5 4 times. So that's going to be 20 just from the 5. And then you're going to add each of the numbers on the edge twice. So the 4 plus 6 is 10, and the 2 plus 8 is 10, that makes 20 for the edge pieces, but they're going to each be added twice. So we have 20 times 2 from those. And then the corner pieces each get added once. So 1 plus 9 is 10, 7 plus 3 is also 10, so we have another 20. So altogether we have 4 20s, which is 80. That's our answer here. All right, let's move on to problem 19. This one says the average of 10 numbers is 9.5. And if 1 is added to the first number, 2 is added to the second, 3 is added to the third, and so on until 10 is added to the 10th, what is the average of the 10 new numbers? Okay, so one way to do this is to think about the average of the numbers you're adding, the average of the numbers from 1 to 10. So the sum of the numbers from 1 to 10 is 55, which means the average is 5.5. And I can just add these two averages, right? So 9 plus 5 was the average of the original numbers. 5.5 was the average of the numbers I added. So the new average will be the sum of those two averages, and that will be 15. So that's our final answer here. Another way to do it would be to think of, okay, if the average is 9.5, that means there's 95 as the sum. And then the sum of the numbers I'm adding is 55, right? And so that's going to give me a 150 for the sum, and then I just have to divide by 10, and that will get me back to the 15 for the average. Okay, let's go on to number 20. This one says m and n are positive integers such that m to the n is 64, and they want to know what is the sum of all possible values of m plus n. So I'm going to write down the prime factorization of 64, and it's just 6 2's, right? 6 2's like this. So if I consider them separately, that's just going to be 2 to the 6th, which is one way to put, one way to get it to fit into this m to the n. But another thing I could do is I could pair these up, right? So I could have these two and these two and these two, and that would give me 4 cubed, right? 4 cubed. And there's yet another way to do things where I could look at these 3 together, right? That would give me 8, and then these 3 together would give me 8. So that would give me 8 squared. And then the last way to do it would be to take them all together, and that would be 64 to the first power. That's another legitimate way to write it as m to the n, where they're integers, right? 64 is an integer, 1 is an integer. So we need to compute m plus n for each of these 4 possibilities. So 2 plus 6 is 8, 4 plus 3 is 7, 8 plus 2 is 10, 64 plus 1 is 65. So these 3 add up to 25, and then 65 and added to 25 will give me 90. So 90 is my final answer on this problem. All right, let's move on to 21. This one says Adam has 5 different sized matchsticks whose lengths are positive integer number of centimeters. No 3 can be arranged to form the sides of a triangle. What is the least possible sum of the lengths of all Adam's matchsticks? Okay, so when you say that no 3 can be arranged to form the sides of a triangle, that means if you take the longest side of the triangle, the other 2 sides are going to add up to something that's less than the longest side. Because if those 2 sides added up to something that was, I should say, it's less than or equal to. So the 2 sides, when you add them together, will be something less than or equal to the length of the longer side in order to not form a triangle. Because if they were bigger, if these 2 sides together were bigger than this, they would be able to reach and form a triangle. So for example, they might go all the way to here and all the way to here. In order to make that triangle, you have to be able to reach all the way from one end of this segment all the way to the other with some to spare. That will form a triangle. So what we're saying here is that none of these 5 numbers can work like that. And we want these integers, they're integers, we want them to be small. We can start with just using the 3 smallest integers, 1, 2, and 3. Those don't form a triangle because the sum of the 2 small ones is equal to the bigger one, and it's not bigger than the bigger one. But if we try to add 4 in here, suddenly we can make a triangle, right? You can make a triangle with 2, 3, and 4 because 2 and 3 add up to something bigger than 4. So we can't add a 4 in there. What if we add a 5 in? That's fine because no pair of these 2 is bigger than 5. And you might spot the pattern. You just take the 2 biggest, you add them up. That'll be the next one you can add in. So adding 2 and 3 gives us 5. Adding 3 and 5 gives us 8. And now we have 5 matchstick lengths, no 3 of which can form a triangle. And of course, this is the Fibonacci sequence, so we could go past that if we have that sequence memorized. And now we just need to add these all up. So we have these are 6, and 5 is 11, and 8 is 19. So our answer is 19. There's also a little trick if you have a subset of the Fibonacci sequence where you can take the last element in your subset and then go 2 beyond it and find that value, and then take the second value in the subset and subtract those two, and that will be the sum of your sequence. But that's a lot of work here. It's easier to just add these numbers up. Here you'd have, let's see, 5, 8, 13, 21. You would have 21 minus 2, and that does in fact give you 19. So maybe if we had a big long list of Fibonacci numbers, that would be a quicker way to add them up. But in this case, it was really easy to just add these numbers. Okay. Suppose x is a real number such that 2 to the x equals x plus 3. All right, so we got this thing. What is the value of the expression below? 2 to the 2 to the x divided by x plus 3. So let's start working this out. 2 to the, I'm going to substitute for this 2 to the x, I'm going to substitute x plus 3 because we know they're the same thing. So this is 2 to the x plus 3 instead of 2 to the 2 to the x. And we're dividing that by x plus 3. Now this is equal to 2 to the x times 2 to the 3, which is just 8, divided by x plus 3. And now we know that 2 to the x is equal to x plus 3, so we can actually cancel these two things out because they're equal to each other, right? We have this from up here. We wouldn't be able to do that if x plus 3 were 0, but 2 to the x, we know that's not 0 because 2 to the anything is positive. So we can cancel those out, and that just gives us 8, which is the answer to this problem. All right, let's move on to problem 23. So this says the square root of 6 plus 2 root 5, all that under the square root, can be written in simplest radical form as a plus square root of b, where a and b are positive integers. Okay, so we know this thing is positive, and it says what is the value of a plus b? Well, since this thing is positive, we can square both sides, and they'll definitely still be equal to each other. So 6 plus 2 root 5 is equal to a squared, I'm squaring this thing, a squared plus b, that's this part squared, and then plus 2a square root of b. So now we have on each side, since we know these things are equal to each other, we can take a look at this and we can say, okay, we've got an integer part over on this side, that's 6. And then we've got an integer part over here because a and b are positive integers. So this a squared plus b, that's going to be an integer. And then we've got like an irrational part, 2 root 5 here, and that's got to be equal to this irrational part over here. So it's pretty straightforward from that point, right? Because these two have to equal each other. You've got square root of 5 equals a root b. So a is going to have to be 1, and b is going to have to be 5. And fortunately that works over here because a squared is 1, b is 5. You add those together, you get 6. So those are our solutions for a and b. What do they want to know? They want to know a plus b, so we just add these together and we get 6. And that is the answer to problem 23. Let's take a look at problem 24. This one's a tricky one. It says how many ordered pairs of positive integers m and n are there with n less than or equal to 10 and where you satisfy this inequality. So you could, one way to do this is to kind of plot things out. You could put like an m-axis and an n-axis, and then you could think about, okay, if m over n is less than 1, you're going to have a slope 1 line that you're going to have to be below or above, depending on which one is m and which one is n, and then you're going to have a slope 2/3 line, maybe like this, right? And then you're going to have to be between them, so you're going to have to be like in this area here, and it says less than or equal to this one, so you're allowed to be on this line, but you're not allowed to be on this line. You have to be actually strictly below the other line, and then you can figure out how many ordered pairs there are. And that works. You're bounded by 10. So let's see, I think that means you're bounded by 10 here, and of course that means the other one has to be 9 or less because it has to be less than. But another way you could do it is just figure out what these bounds are for each case of n. So let's just consider all the different cases for n. We've only got 10 of them, right? Or from 1 to 10. We can start with n equal 1, right? So if n equal 1, yeah, m has got to be less than n, so that's not going to work. Right away, there's no positive integer less than 1, so that doesn't work. N equal 2, that's also not going to work because now m is going to have to be less than 2/3. N equal 3, that's also not going to work. Well, no, n equal 3, let's see, if n equals 3, now I have, if I rewrite this equation with n equal 3, I have 2 over 3 is less than or equal to m over 3, which is less than 1. Okay, so m's got to be less than 3, but it's got to be greater than or equal to 2. So m equal 2 works there. So we have one solution for n equals 3. If we have n equal 4, then maybe I should multiply this thing by 3. How would that be? So now I'm going to have 2 is less than or equal to, well, that's going to be kind of tricky. Yeah, so this is going to be m, it's going to be 3m over 4, is that right? N equal 4, and that's going to be less than 3. So, yeah, basically m always has to be less than n. That's what this part means. So if we just keep in mind that part, we don't have to write this part, I guess. So m is less than n, and then m's got to be greater than 8/3, right? So, yeah, so we're going to have one solution there as well. That's where it's 3. M is going to be 3, right? And then for n equal 5, we're going to have a similar sort of thing where we have 2 is less than or equal to 3m over 5. And so m is going to have to be greater than 10/3. So it's going to have to be 4. So m equal 4. And m equal 5 is not going to work because it has to be less than n. So we have one solution there as well. And basically, every time n goes up by 3, we're going to add one more solution. So once we get to n equals 6, we should have 2 solutions. So let's write it out. We got 2 is less than or equal to 3m over 6. And this just becomes 3m greater than 12. That means m has to be at least 4. So 4 counts, but it can also be 5, right? So m can be 4 or 5 here, 4 or 5. So there are 2 solutions there, and we're going to have that pattern where for n equals 7, we're also going to have 2 solutions. For n equal 8, we're also going to have 2 solutions. And then once n equals 9, we're going to get one more. So that's going to be 3 solutions. And for n equal 10, we're also going to have 3 solutions. So we're going to add this all up. We got 3 plus 6 is 9, plus 6 is 15. So altogether there will be 15 of these ordered pairs that satisfy this. Well, it's a bit of a tedious one. All right, let's take a look at this one. This one says equilateral triangles AB and C and CDE have side lengths 14 inches. Okay, so this is 14. This is also 14, and all the other sides of the equilateral triangles are 14, obviously. And it says segment AE, which is not drawn, but I can draw it here, is parallel to BD. So BD is a straight line, yeah, and it tells us BC and D are collinear. And then it says you've got these 2 crossing points, crossing over to midpoints here. G is a midpoint of ED, and F is a midpoint of AB. And now it asks us what the height is, HC. So this is our goal, is to find this length from H to C. and it wants to know what it is in simplest radical form. So the first thing to notice is that h is directly above c because of the symmetry here. So this is going to have the same slope going up as this one has going down, and so this is going to be an isosceles triangle here, and so this is going to be a straight up and down. So h is directly above c. So we know, so basically we want to form similar triangles here. We've got a similar triangle here, right, going from B, C, H, and then we need to add maybe a new point, let's say a new point down here, right underneath G, and we're going to have a similar triangle going across like that. And we can use that to compute this height because, whoops, sorry, this height here, which is our goal, because it's going to be a little bit more straightforward to compute this height, and then we can use the similar triangles to scale it down. So what is this height? Well, first of all, what's the full height? Let's say big H, the full height of this triangle. So big H is going, let me use maybe a different color down in the black here. So big H is going to be equal to 14 times root 3 over 2. And so that means that the little h here is going to be half that, because this is a midpoint up this segment, so it's going to be half as high. So the little h is going to be 7 root 3 over 2. And now we just need to scale that by the ratio of, the ratio of these two triangles. So we can look at the bases of the two triangles. The base of the smaller triangle, let's call that base 1, is equal to 14. And the base of the larger triangle, base 2, is equal to what? Well, it would be 14 plus whatever this is, and it turns out that this distance from C over to this point here, I guess we need a name for that, maybe X. From C to X is going to be 3/4 the way from C to D. You can see that by thinking about, like, basically that's a midpoint, so it should be halfway to the top, and then on the way down, going from E to G should get you halfway down to D. So that's 3/4 of 14. So B2 is going to be 14 plus 3/4 of 14. All right, so now to find this height here, let's call it y, right? So, or whatever. So let's just call it HC. HC distance. It's going to be equal to this height, little h, 7 root 3 over 2, times this ratio of base 1 to base 2. So that's 14 divided by, let's just call this, I guess I could take out the 14 here. This would be 14 times 7/4. 14 times, I'm going to put the 7/4, I'm going to put the 7 here and the 4 here, because 7/4 if I can wrap it up over there. So we can start canceling some things. Let's see what we can cancel here. So certainly the 14 and the 14 can cancel. The 7 and the 7 can cancel. The 4 and the 2 will just leave me with a 2 here. And all I'm left with is 2 root 3. So that is my answer to this problem. Okay, let's go ahead and move on to problem 26. This one was a tough one. It's kind of tedious. So it says, how many ordered triples of positive integers a, b, c are there for which a plus b plus c equals 49 and a is less than b is less than c? So one way to do this is to think about what all the possibilities are for a, and then given a, what are all the possibilities for b? Once you have a and b chosen, c is fixed, right? So you kind of just have to take all the possibilities for a. One thing that might simplify things a little bit is if we subtract 1 from each of the numbers and divide by 2. So we could call x a minus 1 over 2. The reason I'm doing that is now I don't have to worry about odd integers. If I subtract 1, I'll get an even integer, and then I divide by 2, I'll just get an integer. So if I do this, I'll have y is b minus 1 over 2, and z is c minus 1 over 2. You don't have to do these substitutions. It just makes it a little bit easier. So if you do that and you plug this all in, you get x plus y plus z has got to be equal to, well, if we when we subtracted 1 from each of these, that brought, we had to subtract 3 over here, so that brought that down to 26. And then when we divided them all by 2, that would divide this by 2 as well. Did I say 26? I meant 46. Divided by 2, it'll be 23. So x plus y plus z has to be 23. And what do x, y, and z have to be? They have to be basically non-negative integers. So the first odd is 1, right? So if a is 1, this will give you x is 0. So x can be anything from 0 on up. Well, how high can it be, right? So y is the middle one. Well, let's see. What's the, yeah, x has got to be less than a third of this. In fact, y, yeah, if they're, yeah, like, let's say I made x 6, right? That would be, the smallest I could make the sum would be 6 plus 7 plus 8, right? What would that be? 15 plus 6 is 21. So that would work. But as soon as I made x 7, now I've got 7 plus 8 plus 9. That's going to be 24. It's going to be too high. So the biggest x can be is 6. So x can basically be from 0 up to 6. And basically we just have to, we've got 7 cases for x, and basically we just have to look at each one independently. There's not, you might think there's a pattern, but it turns out that not much of a pattern here. So let's consider those separately. Maybe we can make a table x, x, and then once we know x, we can maybe find what, let's see, we can find what y plus z has to be by subtracting 23. And then from that, we can find the y range. And then from that, we can figure out the number of y possibilities. So that's going to be a useful table. So let's go ahead and fill in our 0, 1, 2, 3, 4, 5, and 6. Almost running out of room there. So y plus z is going to have to be 23 here if x is 0. It's going to have to be 22 here, 21, 20, 19, 18, and 17. So the y range, so if x is 0, y has to be at least 1. And then if you add it with z, which is bigger than y, and you get 23, that means it can go all the way up to 11. So there are 11 possibilities for y. If x is 1 and y plus z is 22, y can start at 2 and it can go up to 10 is the biggest it can be. Because if you're 11, then you don't satisfy the x less than y less than z. They have to be, yeah, because a, b, and c have that, then x, y, and z have to have that. So that gives us, well, that only gives us 9 possibilities. And then here, if y plus z is 21, so the y range is going to go from 3 up to what? It can go up to 10. So that gives us, I guess, another 8 possibilities. And then if it's 3 and y plus z is 20, we can go from 4 up to 9. Okay, so 4 up to 9, that should be 6 possibilities. And then for x equals 4, you have a sum of 19. You can go from 5 up to 9. And 5 up to 9, that is 5 possibilities. And then here, if x is 5, we can go from 6 up to 8. That is 3 possibilities. And finally, if x is 6, the y plus z sum is 17, then y can go from 7 up to 8, which is 2 possibilities. So now we just add up all these numbers, right? So here we have 10, and here we have another 14. That gets us up to 24. And here's another 20. That should get us up to 44. So 44 is the answer to this one. Yeah, a little bit tedious, but we got the answer. All right, let's take a look at number 27. This one can be done a couple different ways. And you do have to make sure that you look carefully at this thing. It says, let 2 to the n be the greatest power of 2 that divides the expression shown. What is the value of n? So first of all, be careful when you're looking at this. You've got these 4 numbers multiplying together, and then you've got a plus, and then you've got another 4 numbers here. So 1 through 4, and then 2 through 5, and then 3 through 6, all the way up to 25 through 28. So you've got these groups of 4. And one thing you could do, one way you could approach this would be to say, for each of these groups of 4, what is the greatest power of 2 that divides it? And one pattern that you'll notice, since you have 4 consecutive integers in each of these groups, 2 of them will be even. And not only that, exactly one of them will be divisible by 4. The other one will not be divisible by 4. So basically, you'll have like an odd times an odd times, you know, some number that's divisible by 2, right? So that's even. And then the other one will be a multiple of 4. I'll just put M4 for multiple of 4. So when you multiply these all together, it's going to definitely be divisible by 8. So it's going to be a multiple of 8. Let's say that. It's going to be a multiple of 8. Now, it may also be a multiple of 16. So for example, if this multiple of 4 is a multiple of 8 also, then the product of this altogether will be a multiple of 16. And you could kind of, you know, you could kind of figure that out by writing down what the 2 even integers are for each of these sets of 4. So for the first one, you'll have 2 and 4. For the second one, you'll also have 2 and 4. And then you'll have 4 and 6. And then you'll have 4 and 6 again. And then you'll have 6 and 8. And then you'll have 6 and 8 again. And then you'll have 8 and 10. And then you'll have 8 and 10 again. And so all of these ones are going to be multiples of 8. And all of these ones are going to be multiples of 16. And actually this pattern is going to continue. And you might think, oh, maybe I can get more powers of 2 because look, I've got 4 multiples of 8. That means the whole sum here is going to be a multiple of 32. And here I've got 4 sums of 16 that are multiples of 16. So this whole sum will be a multiple of 64. And yeah, that's true. So you're going to have 4 groups of 4 numbers, and then the second 4 groups of 4 numbers, and then the third 4 groups of 4 numbers. That sum is going to be a multiple of 32. And the next one, actually the next one might be a multiple of 128, right? But in any case, you're going to have 6 of these sets of 4 sets of 4. So something like this, and that'll get you up to 24 of these sets of 4, right? But the thing is, there are 25. There's this extra one here. And so, yeah, all these things, when you sum them up, they're going to be multiples of 32 or 64 or what have you, right? All the way up to the 6 sets of 4 sets of 4. But then this last one, number 25, is just going to be this product. And how many powers of 2 are in this one? Well, 26 only has 1 power of 2, and 28 only has 2 powers of 2. So it's really just divisible by 8. It's a multiple of 8, this last term that you're adding. So it doesn't matter if all these other things you can figure out, oh yeah, there are multiples of 32. The last one that you add on is only a multiple of 8. And so that means the whole thing is not a multiple of 16. It's only a multiple of 8. So they're asking, the question is what, 2 to the n is the greatest power of 2 that divides the expression shown. They want to know the value of n. So the value of n is just 3 because it's a multiple. 2 to the 3 is 8. So that's the answer to that one. Now I'm going to show you a different way to do this one actually. It's kind of a little more elegant maybe, but also maybe a little more confusing as well. So yeah, definitely a little more confusing, but I'll show it to you anyway. So one thing you might notice if you look at these, you might start thinking about n choose k, right? When we have n choose k, that's equal to n factorial divided by k factorial, and also divided by n minus k factorial. And the form of this is similar to some of these sets of 4, except you have to get rid of one of the factorials on the denominator. But the thing is, it's always the same factorial in the denominator. It's always 4 factorial. So, for example, this first term, you could write, if you wanted to, as 4 factorial times 4 choose 4. It's a little weird thing to do because it's just 4 factorial, but we're doing that to make it a pattern. The second one is going to be 4 factorial times 5 choose 4. And then the third one here is going to be 4 factorial times 6 choose 4. And then plus dot 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 all the way up to 4 factorial times 28 choose 4. And of course we can pull the 4 factorial out. That gives us 4 factorial times 4 choose 4 plus 5 choose 4 plus 6 choose 4 plus 7. Well, I'm just going to do a dot 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 at that point, plus dot 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 28 plus 28 choose 4. And the thing is that we need one more trick here, and that is that when you add up all these n choose 4s, you actually get something that's an n choose 5. So let me show you why that is. Let's say that I wanted to figure out what 29 actually. Let's say I had 29 choose 5, right? So imagine I had 29 objects here. There's 29 of these things. And I had to choose 5 of them. Well, we could use our formula for 29 choose 5, but there's an interesting little thing you could think about it to break it down into cases. You could say, well, what if the last one was one of the 5 that I chose? Then how many options would I have? Well, if you've already chosen the last one, then basically you have 28 left and you need to choose 4 of them. So that's 28 choose 4. And then you can say, okay, well, what if the last one that's chosen is not the very last one in there, but the last one that's chosen is instead the 28th one? Then how many different ways can I choose? Well, if you know that the highest one that's chosen is in the 28th spot, then, and you know that's the highest one that's selected, then you know the 29th is not selected, and you have to choose 4 from the remaining 27. So we could add that in. That's 27 choose 4. And you could keep doing this. 26 choose 4 would tell you how many there are where the highest one is in the 27th spot, and so on all the way down. And basically that would cover all the ways to do 29 choose 5. So this is just a way of proving that this sum here is actually equal to 29 choose 5. So that's kind of nice. And we can figure out what power of 2 29 choose 5 is divisible by, because we have a formula for 29 choose 5, right? So 29 choose 5, well, oh, we need to multiply by 4 factorial as well, so don't forget that. So basically we've got, so let's put the 4 factorial here. We need 4 factorial times 29 choose 5. So this is going to be 4 factorial times 29 factorial divided by 24 factorial, and also divided by 5 factorial. Okay, so this is going to be equal to, I can cancel the 4 factorial with the 5 factorial, and that leaves me with just 5. And I can cancel the 24 factorial with the 29 factorial. That leaves me with 29 times 28. Well, let's just write it out over here. So I've got 29 times 28 times 27 times 26 times 25. And that's all divisible by 5. And of course, I can cancel a 5 here to just give me 5 here. And then now I have an integer, right? And I just need to know how many powers of 2 there are there. I've got an odd number there, I've got an odd number there, I've got an odd number there. So it's just 28 and 26. So 26 has got 1 power of 2, and 28 has got 2 powers of 2. So altogether I've got 3 powers of 2. So that's just a different way to solve the problem. In my mind, it's a little more complicated, but maybe you could say it's a little more elegant as well. Okay. Let's go on to problem 28. So this says, what is the first non-zero digit of the square root of 75 squared plus 1 that appears after the decimal point? Okay, so we've got 75 squared plus 1, and we want to take the square root. I like to do this visually. Imagine you had 75 squared squares, right? So, you know, little blocks. You could, if you had 75 squared, then you could just line them up in 75 rows, right? So just imagine 75 rows and 75 columns, right? So you could just make a square, right? It's 75 squared. That's not very straight, but you could just line them up like this, right? So that's if you had 75 squared. And then, of course, the square root would just be 75. But we've got one extra square. So just imagine you've got this one extra little square here. And you want to find the square root once you add that area into this 75 squared area. So what you have to do is you have to take this one extra square and slice it up, right? So I'm going to zoom in on that square here. Well, no, I don't want to zoom in because it'll make it look bigger. I'm going to slice this thing up into a bunch of little pieces. In fact, I'm going to put one piece on the edge of this first row, another one on the edge of the second row, another one on the edge of the third row. And I'm going to just paint this whole square with these little tiny slivers of this one square. And so in order to do that, I'm going to need 75 different little slivers going up this way. And I'm going to need 75 little slivers across the top. And then, not only that, I'm going to need a teeny tiny little dot right there too to do it perfectly. But I'm not going to worry about that teeny little dot because it's just asking for the first non-zero digit that appears after the decimal point. So we're just not going to worry about that. We're going to just say that I sliced this one square up into 150 slices and I put them all along here. So now basically I've got 75 plus 1 over 150 is my new width here. And then 75 plus 1 over 150 is my new height here. And it's not perfect because of this little dot, but it's very, very close. And so the square root of 75 squared plus 1 is going to be very, very close to 75 plus 1 over 150. So we just kind of need to figure out what this 1 over 150 looks like as a decimal. And of course, if it was 1 over 100, it would just look like 0.01, but it's 2/3 of that, right? So it's going to be 0.006667 or something like that. And all we need to know is the first non-zero digit after the decimal, which is a 6. And sometimes it's good to think about, oh, what about this little dot that we ignored? It might make this a teeny bit different, but the thing is we're not really close to this 6 being a 7 or a 5 because the next digit is a 6. So I don't think we need to worry about that dot. So I think that's probably the quickest way to do this problem. So our answer here is just going to be 6. It's going to be the first non-zero digit after the decimal point. Okay, now we're going on to 29. I actually think 29 was probably the hardest problem on this sprint. So let's see what we can do here. First thing to do, well, let me read this problem. It says, how many ordered pairs of positive integers a, b satisfy this equation? 7ab divided by a plus b equals 2025. Okay, they love to throw the year in. So first thing to do is multiply by a plus b. So we have 7ab is equal to, and let's just expand this out. So we have 2025a plus 2025b, right? And you know what? Maybe we should put everything on one side of the equation. So I'll subtract 7ab. Well, no, I think I'll subtract these two from this side. So let's just go in there and make those minuses, and then we'll put that equal to 0. So we'll get this to be a minus. This will be a minus. So we got minus that is equal to 0. All right, now we're going to use something which is called Simon's favorite factoring trick. So if you have, imagine a rectangle, right? I'm just going to try to prove this to you for a minute. Imagine you have A and B, right? So this side, this side of the rectangle is A plus B. And then on the other dimension you have X and Y. So this is A plus B times X. So this is basically A plus B times X plus Y. And that is equal to AX plus AY plus BX plus BY. Okay, so this one's AX, this one's AY. It's just FOIL, right? This one's BX, and this one's BY. So we would like to try to, you know, turn this into something that looks like this, where we have these two factors. And we can't really do that the way it is, but we can use Simon's favorite factoring trick to try to kind of it's kind of like completing the square. So we're going to need to do a few things. So first of all, we're going to want 7a and 7b to make this thing symmetric. So we're going to have to multiply both sides by 7. So let's see if we can do that. So maybe I shouldn't have erased that, but if we multiply this both sides by 7, we get 7 squared ab minus 2025a minus 2025 times 7a minus 2025 times 7b is equal to 0. And now I can take out the 7a here, right? So I've got 7a times, let's see, 7b minus 2025. And that's basically this part here, right? And then for this part here, I want to take out the 2025, but I need another term here. So what I'm going to do is I'm going to add 25 squared to both sides. That's going to be the fourth rectangle in my Simon's favorite factoring trick. So let me do that with some little eraser magic here. We'll add 2025 to each, 2025 squared to each side. So I'm going to add 2025 squared, and that's going to be equal to 2025 squared. This is a really tricky problem. All right, now I can factor out this thing here into something that looks a little bit like this. So this is going to be 2025. Let's do a minus here. Minus 2025 times 7b minus 2025. All right. So here, this minus 2025 times minus 25, that'll give us the positive 2025, and then the 7b times this will give us this part. So this whole thing has got to be equal to 2025 squared. Okay. Now we can finally factor this completely. and we have 7a minus 2025 times 7b minus 2025 is equal to 2025 squared. And now we've still got a long way to go, because there are a lot of factors of 2025 squared that could be these values here. And we have to consider all those factors. So we basically have to, yeah, well, first of all, let's talk about whether these, they're all integers, right? This is an integer, this is an integer, this is an integer. But can they be negative? So one question is, can this be negative? And one thing you can realize by the form of this is that if one of these is negative, the other one's also going to have to be negative in order to make a positive over here. And the other thing is, the absolute value of one of these two has to be at least 2025 in order to get up to 2025 squared. And if the absolute value of one of these is bigger than 2025 and it's negative, that means that A, or B, has got to be negative. And we know that from the problem, it says ordered pairs of positive integers, A, B. So we know A and B are positive. So that means this can be no less than negative 2025. This can be no less than negative 2025. And in fact, the lowest A and B can be is 1. So really, I guess negative 2018 is the lowest they can be. And so you're not going to be able to get two negative numbers that are going to multiply to give you 2025 squared. It's just not going to work. So that means not only do A and B have to be positive numbers, but when you take 7a minus 2025, that has to be a positive value. And 7b minus 2025 also has to be positive. Okay. So, and not only that, but each of these has to be a factor of 2025 squared. So 2025 squared is going to be 3 to the 8th times, let's see, is that right? 3 to the 8th times 5 to the 4th. Because the prime factorization of 2025 is 3 to the 4th times 5 squared. So when we square it, we get this. And so that means there's going to be a lot of different factors of this 2025 squared. The number of factors is the exponent plus 1 times the other exponent plus 1. So we've got 9 times 5 is 45 factors. 45 factors. And we have to figure out which ones will work in this equation. So we're going to have to just write them all out. And then we're going to use mods to get, to ensure that things work out. So what do I mean by that? Well, this 7a is going to be a multiple of 7. And then this 2025 is a multiple of 7 plus 2. So when I take this multiple of 7 and I subtract a multiple of 7 plus 2, which is what 2025 is, I'm going to get a multiple of 7 plus 5. So that means this thing and this thing both have to be like a 7x plus 5 form. Or this one would be like a 7y plus 5. So in other words, mod 7, these things are equivalent to 5. So we got to find factors. We got to find some of these 45 factors that are integers that have a mod with 7 to give you 5. So basically, we just have to start writing out all those factors and see which ones give you mod 5. So in the interest of not making this video too long, I'm just going to say that if you do that, if you write out all those factors, now you don't have to write out all 45 factors. You just have to write out the ones that are less than 2025, or maybe less than or equal to 2025. Although 2025 doesn't work, you'll find out. So just go up to the ones that are less than 2025, and then you have to figure out which ones of those factors are equivalent to 5 mod 7. And if you do that, you'll find 4 of those factors that work. So let's see. Yeah, so those 4 that work are 243 and 5, which is obviously 5 mod 7. Then 75, which is also a multiple of 7 plus 5. And then 1125. So these are our 4 factors that are less than 2025 that are multiples of 7 plus 5. And so that means they're each going to have a pair that's greater than 2025 that multiplies to give you 2025 squared. And because we could put those, if you take 243, for example, you have 243 and then you have 2025 squared divided by 243. Those two integers can be either A or B. So for each of these 4, I'm going to have 2 ordered pairs. So altogether, I'm going to have 8 ordered pairs. So I skipped the hardest part, which was listing out all those factors and seeing which, finding their value mod 7, their remainder when you divide by 7. But this is one of those problems that probably almost no one gets right. They might guess it right or something, but they don't actually figure it out. And I think they like to have some of these problems in a chapter math counts just so that you don't have a tie. If you have 2 really, really good students, you might have a tie if they both get a perfect score. But some of the last couple problems on chapter math counts are just going to be extremely tedious, just so that you can see who was the guy who finished 26 problems in 18 minutes and had, or maybe 25 minutes and had 15 minutes left over to work on this one problem. So, all right, so that's that one. Now I got one more. It's not as bad as that one. It's problem 30. It says tetrahedron ABCD with volume 2025 centimeters cubed has segment BD perpendicular to plane ABC. Okay, so let's see. So we've got plane ABC. So we've got a triangle ABC here. A, B, C. And obviously those 3 points fall on a plane. And then they're saying that suppose angle ABC is 90 degrees. Oh, ABC is 90 degrees, so that means this one's a right angle. Let's redraw that. So let's draw a right angle here. So B is a right angle in the plane. And then you've got an A and you've got a C, something like that. And then it says DAB is 30 degrees. Okay. Oh, wait, hold on. It said BD is perpendicular to plane ABC. So that means D is coming out of the screen above B. It's perpendicular, straight up out of the screen here. Maybe what we can do to make it easier to draw is we can imagine that face going up the tetrahedron toward the screen here. There's going to be a triangular face here on this edge going up toward the screen. And we can fold that out like this so that we have D here. And then we can do the same thing with this face of the tetrahedron going up there. We could fold that out. So I hope that makes some sense. I've taken these 2 faces and I've kind of cut it along here. So whatever this height is, whatever this DB height is, actually that's what they're asking for, is this BD. So let's just call that X. Whatever that is, it's going to be the same here. So that's the same line. It's just I folded it down here and I folded it to the left here so that we could draw it in 2D. So that distance is X. And it tells us a couple angles. It says DAB is 30. So let's see, DAB. Okay, so this is D here. DAB is this one. This is 30. And then it says DCB is 60. Okay, so DCB. So that means this one is 60. Obviously not drawn perfectly. Okay, and then it wants to know what BD is, and it says express your answer in simplest forms. Okay, so let's find out what the volume of this tetrahedron is with respect to X. So we know the height is X. So first of all, what's the volume of a tetrahedron? It's similar to the volume of a cone or a pyramid. It's 1/3 the base area times the height. That's going to be our volume. And the height is just X. So this is going to be base times X over 3. And what is the base area? Well, let's see. let's call these two edges y and z. And because we have a 90-degree angle here and a 90-degree angle here, y is going to be x times root 3 over 2. But z is going to be x divided by root 3 over 2. So the product zy is actually just going to be x squared. So this base area is just going to be zy over 2. The area of this triangle is zy over 2, but zy is x squared. So this is just x squared over 2. You could do it by putting the root 3's over 2's in there, but it would just cancel out, and you would just get x squared over 2. So now we plug this in for the base into here, and we get the volume is equal to x cubed divided by 6. All right, now we know what the volume is. So let's make some room. I think we don't need the figures anymore. We can just do the math. Okay. We don't even need this anymore. We know the volume is x cubed over 6. And we know that the volume is 2025. So that's equal to x cubed over 6. We can multiply each side by 6 and take the cube root. So that would give us that the cube root, the x is equal to the cube root of 6 times 2025. I'm going to write that as 45 times 45 so that I can start trying to take some factors out of this. So there's a 3 in here, there's a 3 in here, there's a 3 in here, so we can take that out. We get 3 times the cube root of 2 times 15 times 15. And let's see, 15, the prime factorization is 3 and 5, so I've got a couple of 3's and a couple of 5's and a 2. There's no triples in there, so I just need to multiply this out. I can't pull anything else out of the cube root. So 15 times 15, that'll be 225, and then 2 times that will be 450. So the final answer is 3 times the cube root of 450. All right, I hope you guys enjoyed the video. Please make sure to like and subscribe, and I'll be doing the target soon. I already did one short video going over the hardest target problem. The other target problems were not too bad this year, but I will do a video on problems 1 through 7, and feel free to go ahead and check out the hardest problem in my short videos. All right, hope you guys enjoyed it, and I'll see you guys in the next video.